Hello, everybody, to today's specific Quasiworld seminar. So our first speaker is Antoine from Caltech, and he will talk about the geometry of the regular representation of hyperbolic groups. So please, Antoine.
Hi, so thank you for the invitation. Hi, everyone. Let me make it full screen again. Okay, so right, I'm going to talk about the just the regular representation of hyperbolic groups and what you can say about its geometry. So I have to say that looking at the previous talks, I feel like my talk is going to be slightly off topic, and so you should feel free to give me feedbacks about whether or not it's just too quick or too slow. All right, let me start. So I'm going to talk about hyperbolic groups, and as you probably know, they form a very big and important family of groups, and they're defined as finitely generated groups which have negative curvature in some sense. I'm only going to consider in this talk torsion-free hyperbolic groups, meaning that non-trivial powers of non-trivial element is non-zero, non-trivial. You can think of free groups as very special cases of hyperbolic groups. And already in that case, some of the things I'm going to talk about is non-trivial. So you can keep that in mind. But as a geometer, I like another kind of hyperbolic groups coming from Riemannian manifolds. So if you look at the closed Riemannian manifold with negative sectional curvature, then automatically its fundamental group is torsion-free and hyperbolic. So this forms actually a very big family of torsion-free hyperbolic groups, thanks to the work of Charney Davis and Antoine. In fact, you give me any manifold, they have this procedure called the hyperbolization procedure that modifies the manifold until it becomes a manifold with negative scalar curvature, sectional curvature. And you can so construct a lot of them. So let gamma be a forever torsion-free hyperbolic group. There are many ways to study it, considering its subgroups, its actions on nice spaces. You can look at it from a metric geometry point of view, from a growth topology combinatorics point of view. So today I'm going to take a representation theoretic point of view, and you can think of it as a way to, it's a special case of studying gamma from the point of view of actions on nice spaces, right? Because I'm going to consider the regular representation is just going to be a group action on a certain Hilbert space. And actually, this is the definition of the representation I'm going to consider. So there's this canonical linear representation of gamma on the space of L2 functions on gamma called the regular representation. I'm going to denote the regular representation as usual by lambda gamma, which is defined in the following natural way. So if you give me a group element G and a function f, you can act on f and get a new function, which is defined by the following formula. So this is just the action by translation, right, on L2 functions. Is there any question on this? Because everything else is going to depend on the regular representation. All right, so the basic objects of this talk are going to be gamma and its regular representation. The regular representation induces an action on the unit sphere of L2 functions, right? And moreover, this action is free and proper. So this is something you can check. So you have this nice action of gamma on this unit sphere. And so you can consider the quotient, right? The spherical quotient is just this unit sphere over gamma. it is a smooth infinite dimensional Riemannian space. So locally, it's just isometric to a Hilbert sphere. Its diameter is at most pi because well, it's a quotient of a sphere. It's actually a K gamma 1 space. So in particular, the fundamental group of this space is just gamma, right, by construction. That follows from the fact that S infinity, this infinite dimensional sphere is contractible. And you can think of it as an infinite dimensional locally symmetric space of the simplest kind. So I think from this point of view, it really makes sense to try to say something about those spaces. Let me also mention, I forgot to mention, but if you want to study the representation theory of hyperbolic groups, you can take the route of looking at operator algebras, C-star algebras and things like this. So this is not something I'm going to do today. I'm going to take a much more geometric point of view. And the goal of this talk is going to try to study the geometry of this locally symmetric space, this spherical quotient, S infinity over gamma. All right, but what does it mean to study the geometry of this space? What we can do is to use finite dimensional objects inside this space to try to probe its geometry and say something. So for instance, we're going to consider, loops or surfaces or higher dimensional surfaces and use their areas to say something about this ambient space. So is there any question? All right, so that's the goal. Let me start with what you can say about its one-dimensional geometry, so the injectivity radius. If you fix a point in this spherical quotient, the injectivity radius at this point x is basically the infimum of the length of homotopically non-trivial loops based at x. Okay, so of course, this spherical quotient locally is just a sphere, but so you can try to look at how non-collapsed or collapsed it is at every point, and this information is given by the injectivity radius. Now, if you fix a scale, so if you fix a number epsilon, you can define its epsilon thin part. So the epsilon thin part is the set of points in this space where the injectivity radius is at most epsilon. A remark here, so the injectivity radius in this space is always strictly positive, of course, because again, this is a quotient of a sphere that's locally just a sphere, but this function, this injectivity radius can be arbitrarily small. So this is a first situation where this space is more complicated than what it looks. So let me try to explain that little remark that you have points where the injectivity radius can be as small as you want. It's not too complicated to explain, so let me try. You fix a group element G, which is non-trivial, and let's consider a function in L2 of, say, unit norm, supported on this finite set, 1G, etc. So powers of G, and equal to 1 over square root of n on those points, and 0 everywhere else, right? So this is this finitely supported function, and it's only supported on those powers of G. Then you can check that if you translate this function by G, so if you act by the regular representation, the new function that you get is going to be very close in L2 to your original function if this n is very large. So in other words, the limit of the distance between the image of Fn and Fn is going to 0. So what this means, if you translate that in the quotient space, it just means that the injectivity radius at the point corresponding to Fn is going to 0. Right, so this is one simple but quite typical phenomenon that appears in this spherical quotient, and we're going to see more complicated versions of this phenomenon later. I'm going to remind you about the classical Margulis lemma, just to warm up. So let's consider a closed Riemannian manifold with negative sectional curvature. Say the sectional curvature is between -a and -b, two negative numbers. Then Margulis lemma tells you that the epsilon thin part of this space has very simple topology. So it states that there is an epsilon depending only on the dimension, depending only on the dimension and A and B, so that the image of the pi1 of a connected component of the epsilon thin part inside the whole group is a cyclic subgroup. Maybe I should add, oh, so it's either 0 or Z. So I didn't include a picture here, but you should then imagine that in any closed Riemannian manifold of negative curvature, the thin part has fundamental group cyclic subgroup, cyclic group. So this is well known. And let's see our first property that I want to talk about today about the spherical quotient. So as usual, gamma is distortion-free hyperbolic group. And the first property I want to say is that you have a Margulis lemma for this space. In other words, if epsilon, depending only on gamma, is small enough, then the image of this map, as before, is a cyclic group. So the epsilon thin part of this space is very simple. Property 1 is not too hard to show, but we're going to see a much more difficult or property, so property 2, which is in spirit related to property 1. And since I can try to explain the proof of property 1, I wanted to include it here. A remark is that actually the proof of this, of course, is going to be completely different from the classical case of negatively curved manifold, simply because this is a spherical quotient. It's positively curved, and it's also not even locally compact. Remember that in the proof of the classical Margulis lemma, you need some compactness at some point. So if there's no questions on the statement of this property, I'm going to move on to higher dimensions. So this property is really about one-dimensional information. All right, so it seems that it's clear. Let's move on to higher dimensions. The injectivity radius, okay, it's one-dimensional. What can you say about higher dimensional surfaces? Here, we're going to be very interested in k-dimensional surfaces in this spherical quotient, which minimizes the area or almost minimizes the area in their homology or homotopy class. In the same way that for the injectivity radius, we actually care about almost length minimizing loops. Now, let's assume here that this spherical quotient admits some non-trivial homology class. Otherwise, it's hard to say something. Actually, even if there's no non-trivial homology class, you can try to do something similar. But for simplicity, let's assume that you have a non-trivial homology class in, say, dimension k. For instance, if gamma is the pi1 of a negatively curved closed manifold, then automatically you have a non-trivial fundamental class. You have a non-trivial canonical k-dimensional homology class in this spherical quotient, right? Remember that S infinity over gamma is a k pi 1 space. Another remark here, so actually this spherical quotient never contains any area minimizing surface of any dimension in any homology class. This is something that's quite counterintuitive if you know about minimal surfaces or geodesics in finite dimensional manifolds. But so here, I'm not going to explain that too much, but there's just no area minimizing surfaces. By the way, by area minimizing, what I mean is you have your surface, k-dimensional surface in your homology class, and you try to deform it continuously. And if every time you deform it, you get a bigger area, then you say that your surface is area minimizing. So this remark is kind of related to the fact that the injectivity radius on this space is not lower bounded from 0. In fact, given any surface in this spherical quotient, you can always strictly reduce its area by spreading it inside L2 in the same way that we did with the injectivity radius. So it makes more sense to consider almost area minimizing surfaces. So those kind of surfaces are going to be more useful. Here's the definition. Given eta, a positive number, and a closed k-dimensional surface in this spherical quotient, we're going to say that it's eta almost area minimizing if for any competitor sigma prime homologous to sigma, you have that the area of sigma is bounded from above by the area of sigma prime plus eta. So up to an error eta, sigma is already more or less area minimizing. So this is the kind of surfaces that are going to be more interesting to consider here. Again, let me know if you have questions on this definition. So you want to try to say something non-trivial about the areas of such almost area minimizing surfaces. And now we come to property 2, the second property I want to talk to you about. And it says the following. It's a kind of avoidance property. So let eta and epsilon be two positive numbers and sigma be an eta almost area minimizing surface. Then the claim is that the area of the intersection of sigma with the epsilon thin part is bounded by some function f that converges to 0 as epsilon and eta go to 0. So let's unpack this statement. Basically says that if eta is almost area minimizing, it will try to avoid epsilon thin parts if epsilon is very small. It will have very small area in the epsilon thin part. Right, so I reformulated this as almost area minimizing surfaces tend to avoid the thin part of your spherical quotient.
So a quick question. As you mentioned, I mean, these are all somehow infinite dimensional phenomenon.
Yeah.
Is there still any kind of finite dimensional cartoon that one could possibly have in mind that somehow illustrates this?
So that's a good question. I thought about that and I couldn't find a good, convincing finite dimensional situation that's well known. And of course you can, let's see, you can cook up some. No, I don't have a good example that's simple to explain.
Yeah, fair enough. I mean, infinite dimensional spaces are a bit hard to visualize, right?
That's right. But in some sense, it sounds scary, but in the end, it's just it's okay, a manifold of infinite dimension. Let's see.
Well, I mean, the statement is clear enough. So.
Yeah, okay, cool. And yeah, so I want to emphasize, later I will try to explain why this is a very non-trivial statement, actually. Because it's very easy, of course, to construct artificial examples of metric spaces where this is completely false. Okay, so property 1, this Margulis lemma, and property 2 are the two things I want to try to explain to you today as, I think, examples of what I mean by trying to understand the geometry of the spherical quotient S infinity over gamma. So in the course of this explanation, I hope to discuss some general properties of the regular representation of those groups and their limits. So here's the outline of the remaining of the talk. In order to give an idea of how this Margulis lemma and this avoidance property are shown, I will first describe a general lemma about limits of regular representations. And then I'm going to need the notion of ultralimits. So that's going to be, take some slides. I'll try to explain the definition for those of you who are not used to this notion. And then I'm going to introduce some deformation maps, some one-Lipschitz maps that are very useful if you want to prove things like the avoidance property. All right, so one first tool that's going to be helpful in this discussion is the following lemma. And I think it's an elementary lemma, but I couldn't find it in the literature, and I talked to many group theorists. And apparently it's new, but if someone in the audience already knows about that or thinks that it's somewhere or trivial, you should definitely let me know. So what is this tool number 1? Let gamma be hyperbolic torsion free. And let's consider two sequences of group elements, Gj and Hj, such that they do not commute, okay? And consider two sequences of functions Vj and double Vj in this unit sphere in L2. The statement is that if the distance between, so you move Vj with Gj and you look at the distance to Vj, if that converges to 0, and if you have the same thing for Hj and double Vj, then the conclusion is that the distance between Vj and double Vj as vectors in this sphere is going to converge to pi over 2. So in other words, if Vj is almost fixed by Gj, if double Vj is almost fixed by Hj, and Gj does not commute with Hj, then the distance between Vj and double Vj is going to be more or less pi over 2. Right, so I'm going to make more comments about this tool, but why is this tool important? It's because it's going to be the basis of more or less all the technical tools that I'm going to talk about later. So it's good to try to, to understand this basic statement. Another way to summarize tool 1 is that if you have two functions, uv of norm 1, which are almost fixed by two non-commuting elements of your hyperbolic group gamma, then they're almost maximally far apart. So they're at distance pi over 2 in the sphere.
So is there no finite dimensional analog of this? Is this again a strictly infinite dimensional phenomenon?
Okay, good question. I haven't thought about that, but really the proof actually depends a lot on the fact that you're considering the regular representation, which okay, of course, force is infinite dimension, but as you say, maybe there's again a better way to illustrate that in finite dimension that I do not know of. Yeah. Well, let's see. But let's try to.
Can I ask, this is still true if Vj and Wj together have fixed a finite support in the index J? They're in some finite dimensional object, right?
Oh, no. So let's see. Vj and double Vj are sequences in this infinite dimensional sphere.
Yeah.
But they could have finite support or infinite support, right? They're just in L2.
Okay, so if they had finite support, wouldn't you have a finite dimensional theorem?
But in the end, you're considering the action of the group.
Okay, moving them around.
And so if you iterate, say you take a group element and you iterate its action, it's going to move around the support. And the support, even though it's itself finite, but it's going to cover an infinite
No.
infinite set.
Okay.
Right.
Thank you.
Thanks for the question. Let me try to give you some intuition about this statement. For free groups, if you know about free groups and you think about group theory, then probably you can just prove it simply. And it goes like this. So if you look at a function in L2, which is almost fixed by a group element in the free group. So here gamma should be fk. So you think of v as a function on fk, which is in L2 of norm 1. And if it is almost fixed by translation by an element g, then v is going to be almost constant on subsets of the form that I'm writing here. So basically x times the power of g, right? So this is more or less by definition of being almost fixed by g. Now, if you have another element double v, which satisfies the same thing, but for another group element h, which is not g and which does not commute with g, then you can imagine that those two functions, they have to be supported on completely different subsets, essentially, if that makes sense. A cleaner way to prove this lemma is to look at the group action of your free group on the Cayley graph. Probably that's the cleanest way. For general torsion-free hyperbolic groups, I don't think, at least I couldn't find a very simple proof. And the proof uses really Delzon's theorem on free subgroups of gamma. So for general hyperbolic groups, say torsion-free hyperbolic groups, there's this theorem of Delzon that tells you that you take any two non-commuting elements and you can build a free group from powers of those two elements. And this power is uniformly controlled depending on the group. For those of you who maybe have heard of it. And it turns out that it's important to use this theorem. And basically, this is the explanation for the lemma. So let's see if there's any questions. Now, remember that, okay, that was my question. Maybe it's in the literature somewhere, but I asked it a lot of people and didn't have a positive answer. And remember that we were interested in this Margulis lemma, saying that the pi1 of the epsilon thin part is actually just a cyclic group. And this is a corollary essentially of tool 1 of this lemma, because if you take a point x in this spherical quotient, and if there are two very short non-trivial loops, gamma 1, gamma 2, based at x, you would like to say that those two short loops correspond to elements in the same cyclic subgroup. This is what you want. And how does it go? Well, as group elements, gamma 1 and gamma 2, they almost fix a function corresponding to x, right? You're just translating the statements about short loops. Then the lemma tool 1 implies that gamma 1 and gamma 2 actually, they have to commute, because gamma 1, gamma 2 are almost fixing the same element. And so gamma 1 and gamma 2 are in the same cyclic subgroup by general properties of hyperbolic groups. So this is an illustration of how you want to study limits of the regular representation and in turn say something about the spherical quotient. And we're going to do the same thing for property 2, and that's going to be much more involved, so I'm not going to explain the details. But if you understand more or less how it works for property 1, then probably you'll get a good idea of how it works for property 2. Any questions on this outline of proof? Okay, let's try to do the same thing for property 2. And there, we're going to need the notion of ultralimit. I'm going to explain why later. But let me first define what an ultralimit is for those of you who don't know. If you have a sequence of metric spaces with uniformly bounded diameter, there's a way that you can make sense of the following limit, the limit of the distance between xi and yi for any sequences of points xi and yi. So of course, in the usual sense, this limit does not always exist, but you can make sense of this limit using the notion of the non-principal ultrafilter. And the ultralimit of the sequence xi(di) is then defined as the metric space, which is the following quotient. X infinity is the space of all possible sequences xi that you quotient by this equivalence relation, saying that two sequences of points are identified is if this limit of, the limit in the sense of the non-principal ultrafilter between those sequences is converging to 0. So it's a huge space. For example, if you start with some separable metric spaces, the ultralimit in general is not going to be separable because you're looking at all possible sequences. Here, we're going to care about the ultralimit of the constant sequence, S infinity over gamma. And it's helpful to know that this ultralimit is still a quotient of a Hilbert sphere by an isometric group action. But this time, the group action is not free, and so this quotient has singular points. Heuristically, what happens is that the ultralimit is going to encode every possible sequences of points. And so recall that for the avoidance property, what we want to understand is the properties of sequences of k-dimensional surfaces. And so considering the ultralimit is useful because it's going to quote unquote contain all the possible limits of those surfaces. a little bit more intuition here. A sequence of points xi in this spherical quotient such that the limit of the injectivity radius is 0 corresponds to a point which is singular in the ultralimit. And vice versa, if you have a sequence of points in the spherical quotient such that the injectivity radius stays bounded away from 0, then that corresponds to a smooth point in the ultralimit. Let's fix some notations here. So you are going to look at the set of singular points in this ultralimit and the set of smooth points. So again, smooth points are just points in the ultralimit such that a neighborhood of this point is isometric to a Hilbert sphere. So the main tool number 2 to show the avoidance property is going to be this thing. It tells you something about the ultralimit of the spherical quotient. So let's read that. For any separable subset A in this ultralimit, there exists a continuous family of one Lipschitz maps from A to this ultralimit. Oops. So these maps, they crucially depend on A, okay? For each A, you have such a family of maps. D0 is the identity, and then D1 of A has the property that D1 of A, yeah, so D1 of A is almost completely contained in the smooth part. So D1 of A intersected with the singular part is just a discrete subset. And again, it's tough to give a finite dimensional example, but in finite dimensional, you can try to imagine your favorite, non-smooth spherical quotient. So just a sphere, finite dimensional, and you quotient it by a finite group action. You get a metric space with singular set, and in general, the singular set is going to be quite complicated. And this statement is definitely false in general, right? It's definitely false that you can always deform a subset to something that avoids almost entirely the singular set. Right, so given a separable subset A, you can deform A in a one Lipschitz way, meaning so all the maps are just one Lipschitz, to a subset that almost completely avoids the singular part.
So this applies in particular to finite dimensional surfaces, right?
Yes, exactly. So we're going to apply this general metric statement to A being surfaces or curves and things like this. But so this statement is, as you can see, relatively easy to state modulo the definition of ultralimits. You have this nice property that you have those one Lipschitz deformations, and they actually say something about the spherical quotient, the original spherical quotient. Let's see. Yes, one remark here is that A really needs to be separable. Remark that the ultralimit itself is non-separable. It's a huge space, and it makes sense that you cannot completely deform the whole space to the regular part. I think intuitively that makes sense. Now, remember that the avoidance property is telling you that if you have a surface that's almost area minimizing, you look at its intersection with the epsilon thin part of your spherical quotient, then its area is small, if the parameters epsilon and eta are small. So we want to prove that using those deformation maps I mentioned, and I'm going to try to explain that. So tool 2 implies this avoidance property because let's suppose towards a contradiction that you have this sequence of almost area minimizing surfaces sigma I with the following property, right? That the area of its intersection with the epsilon I thin part is uniformly bounded away from 0, and epsilon I and eta I both go to 0. Then what you can say is, okay, this is again an intuition, that those surfaces sigma I, they live in the spherical quotient, but they are going to converge to something in the ultralimit. This is the whole point of the ultralimit, is that it's going to contain every limit that you can possibly think of. So now you have a surface, a k-dimensional surface sigma infinity in the ultralimit. And because of our assumption, the area of sigma infinity intersected with a singular part is strictly positive, right? Because our assumption is exactly saying that you have this sequence of surfaces that has a lot of area concentrated in the thin part of your spherical quotient. And remember that the thinner and thinner part corresponds in the ultralimit to the singular points, exactly. So because of tool number 2, you can deform this surface sigma infinity to a new surface such that you have this inequality. And the reason is that, remember that the deformation, okay, let me go back to the deformations here. The deformation is going to send, every deformation map is one Lipschitz, and it's going to send A to something that almost avoids the singular part, and it's something that's implicit here. It's going to send whatever is inside the singular part to a discrete subset. So you're going to apply this tool number 2 to the case where A is this sigma infinity. Anyway, so because of tool 2, you get this new surface that has a lot less area, but then by approximating this new surface inside the original spherical quotient, you get a surface sigma I prime, which has significantly less area than sigma I, contradicting the fact that sigma I was eta I almost area minimizing. So that's the vague outline. It's okay if the details are not understood here, but the main point is that you can use those one Lipschitz maps to say something about the avoidance property. Okay, and I'm not going to say too much about the proof of tool 2, but basically, in order to construct those deformation maps in tool 2, you need to really understand this ultralimit, and roughly speaking, you squeeze the hell out of tool number 1. So you repeatedly use tool number 1 in some ways to understand the singular part of this and of this ultralimit, and realize that it has a very simple structure, quite surprisingly. Okay, boom, boom, boom. Now let me move on. So that was the end of my explanation of property 1 and property 2, and I want to explain some applications to something called the spherical volume of manifolds. So those tools, they have applications to the so-called spherical volume, which is an invariant, a topological invariant due to Besson, Courtois, and Gallo. Let's consider the special case of closed-oriented negatively curved manifolds. Then again, this quotient has a non-trivial fundamental homology class H. And the spherical volume of M is just the infimum of the areas of sigma, where sigma is an n-dimensional surface representing this homology class. Again, so the spherical volume is just this minimum area. And it turns out that it's topological invariant, and sometimes you can even compute it in the case of, for example, hyperbolic manifolds. But in general, it's not a computable invariant. It's not maybe the right question to try to compute it, but you can say something else. And I come from the field of differential geometry where we care about minimal surfaces, so surfaces that minimize the area. And so here's a theorem that's related to this kind of question. It's an existence theorem. It tells you that there exists an n-dimensional area minimizing surface, T, in the ultralimit that exactly realizes the spherical volume, meaning that its area is exactly equal to the spherical volume of M.
Quick question. So
Yeah.
you don't have a minimizer in the original space, right? Because
Yeah.
there's always, you can always make it smaller, right?
That's right. That's right. So that's basically also why you need to consider a bigger space like the ultralimit. But there are many questions as to how to maybe reduce the size of this space. Maybe you can say something more about the limit and not brute force and take the whole ultralimit. But for now, the ultralimit is going to be enough. And the second point is that this minimal surface is going to more or less avoid the singular part. It's going to live in the, up to a discrete subset, it's going to live in the smooth part of this spherical quotient, this ultralimit. Right. So there's this theme in differential geometry that is very old and classical, which is asking for the following. You give me, say, maybe a topological manifold, and you want to construct or cook up an optimal shape or some best metric. And you can do that in not that many cases, actually. So you have a pretty good answer to this question in dimension 2 or for 3 manifolds because of geometrization, or in Kähler geometry because of special methods there. But in general, it's actually really hard to even make sense of this question. But this setting gives you a pretty general result where you can make sense of this particular question and say something. So I like to think of this theorem as saying, that any negatively curved M can be deformed to an optimal shape that has a minimal surface geometry. Right. A few more comments, and let me move on. Yeah, a few more comments about the setting. So this area minimizing surface T is obtained as a solution to a variational problem that's called the spherical plateau problem. So in fact, T is a limit of almost area minimizing surfaces. And this T is constructed by using an important compactness theorem due to Wenger in geometric measure theory. So here, whenever I say surface, actually, I mean surface in the sense of geometric measure theory. So it's not going to be a smooth surface everywhere, but you can think of it as a very nice generalization with a lot of good properties. And by the way, in the end, the area minimizing surface is going to be smooth almost everywhere.
So you are alluding to the theory of currents here? Or?
Yes, that's right. So for those who have heard of it, this is going to be the Ambrosio-Kirchheim theory of currents in metric spaces. And the tools that I mentioned about limits of regular representations and deformation maps, they're really crucial in establishing the following points that look very different and disconnected, but they're proved using the exact same tools. So the first thing is that you want to show that the T is actually a minimal surface, it's area minimizing. The second thing is that you want to show, well, that T avoids almost completely the singular part. And the third thing is this equality, that the area of T is actually exactly what you expect, which is the spherical volume, this infimum of areas of surfaces. So this is maybe a little bit hard to digest, but let me say something more about a conjecture that I think is relevant here. The theorem that I mentioned about T, the existence of T, suggests something better. I claim it's better, and it's the following conjecture, which is that the fundamental group of any closed negatively curved manifold should act geometrically on a very nice space, an n-dimensional minimal surface in a Hilbert sphere. So, right, I'm just going to not say more about this conjecture, but I think it really summarizes what we're trying to do here. We're trying to use the minimal surface geometry as some kind of canonical geometry or optimal space. And proving that would require a much better understanding of limits of surfaces, but also limits of groups and limits of the regular representation, as in tool 1 and 2. I wanted to make some small comments about the Cannon's conjecture. So by the way, I want to make it clear that I don't have any approach to the Cannon's conjecture. So if you are here to hear about a new strategy to prove it, you're going to be utterly disappointed. But I wanted to make some comments on why there are some connections that are interesting to consider. Remember that the Cannon's conjecture is about torsion-free hyperbolic groups whose boundary at infinity is homomorphic to S2. And the prediction is that gamma is actually the pi1 of a closed hyperbolic 3 manifold. And you have actual approaches by Bankleiner and Markovich. Bankleiner is using the language of Alfor's regular conformal dimension, and Markovich is using surface subgroups, basically quasi-convex surface subgroups. So what's the connection between this question and the setup that I mentioned earlier? So we can try to think of the Cannon's conjecture in the setting of the spherical plateau problem, and I'm going to end with that. So that was more or less completely observed by other people. For example, that was observed by Cheatham West and Nolte. First, the theorem that I mentioned about the existence of some minimal surface holds for any torsion-free hyperbolic group gamma with a non-trivial homology class H. So in particular, whenever you have that, then you have a corresponding area minimizing surface T in the ultralimit. That's the first point. The second point is that when gamma is well known, for example, if gamma is the pi1 of a hyperbolic manifold, then you look at this minimal surface, this in this case n-dimensional minimal surface, then the intrinsic metric on this is a typo. So what I want to say is that T is diffeomorphic to M with a hyperbolic metric. So actually you recover the hyperbolic metric. This is something that's really nice, and that comes out from the work of Besson-Quarta-Gallo plus some extra effort. What it tells you is that you have this general minimizing procedure, and if you actually know that gamma is the pi1 of a hyperbolic manifold, then the resulting minimal surface is exactly M with a hyperbolic metric. Okay. And the third point is that if gamma satisfies the conditions of Cannon's conjecture, then gamma is a Poincare duality group of dimension n. So in particular, you have a non-trivial fundamental class H. And so the logic of Cheatham West and Nolte in this context was, all right, so if you satisfy the conditions of Cannon's conjecture, then you can apply this general minimizing procedure. If the conjecture were true, by point 2, you should get as a resulting minimal surface actually your hyperbolic manifold, right? So that's the connection. Is there any question on this connection? So maybe I think the key point here in this connection is to try to understand what happens in this area minimizing problem. So in the spherical plateau problem, you start with a submanifold of the spherical quotient, and you try to deform it to reduce its area as much as possible. And it seems that the key question here is, one key question in relation to Cannon's conjecture is to see whether or not it's possible to show that this area minimization simplifies the topology, right? Because, for example, if you know that the fundamental group of your cycle is exactly gamma, then you're done by Paraman, right? So, but in general, your cycle, your surface has a much bigger fundamental group, but maybe because of this minimization procedure, you'll have to simplify this fundamental group as much as possible. And so in the end, you get that the fundamental group has to be gamma. Okay, this is pure speculation, but this is maybe a guiding question. And for example, even in dimension 2, where things are well known, I don't know how to show this kind of simplification a priori if I didn't know about Cannon's conjecture, right? Right, so let me wrap up. In summary, what we saw was that I was interested in trying to understand the geometry of the spherical quotient, and I'm just using finite dimensional surfaces in the spherical quotient. And we saw two properties, Margulis' lemma and the avoidance property, that are typical of what you can do with this spherical quotient. And the tools involve understanding the limiting behavior of lambda gamma. The theorem is that using those tools and those techniques, you can construct minimal surfaces that correspond to negatively curved manifolds. And you have a bunch of open questions about the limiting behavior of surfaces, groups, and representation. Really, the common theme here is that you want to take limits of a lot of things like surfaces, groups, and representations and look at their interplay. Right, so this is the end of my talk. Thanks a lot for your attention.
Yeah, thanks a lot. Let's thank the speaker. So are there comments or questions? Well, I mean, I already asked a lot of questions, so let me ask another one. So what is the philosophical reason why you want to go to the ultralimit here? Is this that you gain some kind of compactness property, or?
Yes, it's exactly that. So it's just that, you know, when you try to minimize the area, you have the sequence of surfaces, and you want to say that they converge to something. And as we recalled earlier, it's not going to converge to anything in the spherical quotient. So how do you make sense of that? And it's exactly what you said. The ultralimit is a natural metric space that is going to contain something, which is a limit in a very nice sense. And for example, you can take a look at this Wenger's compactness theorem, which is very general, and it's expressed using this ultralimit.
Okay, thanks.